What if I told you that wastewater is a goldmine of valuable compounds like carbon, nitrogen, and phosphorus, essential for creating new circular bioeconomy supply chains? What would you think? If these elements are properly recovered, they can replace synthetic fertilizers, bioplastics, proteins, and other products that are usually derived from non-renewable resources. In this lesson, we'll see how it's possible to rethink wastewater treatment plants and turn them into biorefineries capable of transforming waste into new, sustainable, and circular products. One challenge in this regard is that wastewater often contains these elements in a diluted form, making them difficult to recover. In fact, although they are often concentrated at the source, waste is typically diluted when it is flushed down the drains. Just think that urine, if collected as is, would have a nitrogen content comparable to commercial fertilizers. Yet it gets diluted more than tenfold by the toilet flush. That's why the first step is to collect these elements in concentrated streams, avoiding their dispersal into the environment. And this is exactly the function of wastewater treatment plants which, however, in order to protect ecosystems and public health, usually focus on removing carbon and nitrogen from wastewater by converting them into atmospheric gases such as carbon dioxide, which is also the main gas responsible for global warming, and molecular nitrogen. Therefore, turning wastewater treatment plants into biorefineries first requires minimizing the nutrients released into the environment and transferring them into concentrated streams, such as sewage sludge. This goal can be achieved by introducing innovative technologies or by using conventional technologies differently, so that carbon or nutrients are kept being volatilized. For example, I can mention the use of ion exchange materials to retain nitrogen and phosphorus on their surface and then release them into concentrated liquid streams, or the application of bacterial communities capable of capturing carbon particles present in wastewater within the sewage sludge without degrading them. Sewage sludge itself, which is usually seen as a problem, should instead be reconsidered as a concentrate of nutrients, where carbon, nitrogen, and phosphorus are mainly found in the excess bacterial biomass generated by biological processes. And it is precisely on these that advanced technologies can be applied to extract and add value to them. Speaking of phosphorus, which is a critical raw material, its recovery from sewage sludge can be done after the incineration of the sludge itself, since it becomes concentrated in the ashes from which it can be easily extracted in the form of inorganic salts. These salts can be reused in the fertilizer industry or to produce batteries for electric vehicles. It's even better if the sludge is pyrolyzed, meaning thermally treated in the absence of oxygen, so that the carbon is not released as carbon dioxide but is instead retained in a carbonized form in biochar, a compound that, among its many agronomic properties, can store carbon and return it to the soil. In addition to this, more advanced technologies based on fermentation are being developed that allow carbon to be broken down and reassembled into other compounds, such as volatile fatty acids, thanks to the use of specialized microorganisms and biological reactors. In fact, some of these microorganisms are able to recombine carbon into biopolymers within their own cells, allowing us to produce biodegradable bioplastics by extracting and purifying them. Finally, other microorganisms make it possible to simultaneously recover carbon and nitrogen by synthesizing proteins from the transformation products of sewage sludge. Among the various technological solutions, there are cutting-edge processes that make it possible to gasify sludge, that is, to transform it into a nutrient-rich gas stream free of any contaminants, which certain microorganisms can use as a substrate to develop bacterial biomass with a high protein content. This biomass can then be reused for high-value applications, such as human and animal nutrition. The brief overview of technologies I've presented is just a taste of the existing possibilities that integrate chemical, physical, and biological technologies, with the goal of providing a wide and adaptable range of solutions to replace conventional production processes with sustainable and circular alternatives.